Okay, we're going to talk about Descartes' Rule of Sign, which is one way that we might be able to take the list that's created by the rational zeros theorem and narrow it down a little bit. In order to be able to use the Descartes' Rule of Sign, you need to know what a variation in sign is, okay? What a variation in sign is. The reason why we have to know what this is because this is what we count in the polynomial. Descartes' Rule of Sign will give us an idea of how many positive real zeros we'll have and how many negative real zeros we have. And to figure out how many, we count the variations in sign within the polynomial, okay? A variation in sign happens when one term in your polynomial is one sign and then the next term is the opposite sign, okay? So for example, if we were to take something like p of x is equal to 3x squared plus 7x minus 6, then when you go from a positive 3x squared to a positive 7x, the sign does not vary, okay? So that's not a variation in sign from the first term to the second. But then when we go from the positive 7x to the next term, which is a negative 6, that is a sign variation right there. So we have one variation in this particular polynomial, okay? And it's from this term to that one, positive to negative, okay? Well, it turns out the maximum number of positive real zeros can be found by counting the number of sign variations in P of x. Then after we count them, that will give us the maximum number of positive real zeros, and it actually turns out that they'll either be that number or less than that number by an even number. Okay, and I'll show you what I mean by that in just a minute. Now let's talk about the maximum number of negative zeros and how we find them. The maximum number of negative real zeros is found by counting the number of sign variations or variations in sign in P of negative x, okay? Let me show you how to get P of negative x. We take a look at what P of x is up there. And to get P of negative x, we plug a negative x in for every x. So what you'll see happen in the polynomial is everywhere that the x has an even power, like here where I'm squaring it, or in the terms that don't contain an x, whoops, got ahead of myself there, didn't I? That's supposed to be a negative x in parentheses. The terms that don't have an exponent like the negative 6 here, the constant term, those two terms will wind up not changing sign at all, okay? So if it's got an even exponent, then you won't change the sign of the term. But if it has an odd exponent like this first degree term here, we will see a sign change for those. So you change the sign on the odd powered terms, but not the even powered terms when you swap to this P of negative x. All right, let's scoot down just a little bit more. P of negative x is equal to still 3x squared minus 7x minus 6. Now what happens then, if we did have some terms that have an odd power, we have a change in our sign. So our number of variations in sign may change a little bit too, okay? And you saw up there we had the one variation. Here we also, again, have one variation. So what this means is for the maximum number of positive real zeros and the maximum number of negative real zeros, for this particular P of x that I wrote down right up here in the definition of variation of sign, we wind up having a maximum of one of each, okay? All right, so let's talk about what happens if we don't have the maximum number that we wind up with, okay? Maybe instead of getting a 1 for each one of these, maybe I counted and got 3 variations in sign. You know, what are the alternatives besides having that maximum number? Well, since we're discussing the real zeros here and not the imaginary zeros, it turns out that imaginary zeros happen in pairs, so you always have an even number of them. So if you're looking at how many positive, or not positive, but how many real zeros you have, you can either have the maximum number that you're given by this process, or less than that maximum number by an even number. So in other words, you count backwards. Say if you get 3, then you may have 3 or you might just have 1. If you get 4 of positive real zeros, we'll say, there might actually be 4, or there may just be 2, or there may not be any. Okay, so you can count backwards like that. Let's take a look at an example of how this might show up in a homework problem or on test. Okay, so here we are. We want to find the possible number of positive real zeros and the possible number of negative real zeros of the polynomial. So let's write our polynomial. P of x is equal to x to the 6th minus 5x to the 5th plus 3x to the 4th minus 2x squared plus 9. Okay, now, unlike when we do synthetic division, order is important, but if you're missing terms, that part does not matter, okay? You do want to have it in the correct order. It does need to be in descending order. If it's not, that will change the number of sign variations that you have. You could manipulate that. So we want it to be in descending order when we use the Descartes rule, but it does not have to have any placeholders, okay? In fact, you don't want to put the placeholders in because that may mess you up too. Okay, so let's find the possible number of positive real zeros by counting the number of sign variations that we have in this polynomial. We'll start with our first term right here, the x to the 6th. It's positive. So when we go to the next term is negative, okay? So that is one sign variation there. From negative 5, x to the 5th, to positive 3x to the 4th, we have a sign variation there. So there's 2. And then from 3x to the 4th to negative 2x squared, we have a third one. And then negative 2x squared to positive 9, we have a fourth. Okay, so there are 4 sign variations in P of x. That means that the number of, let's see, trying to find a place to write it. The number of positive real zeros is either 4 or less than that by an even number, which means we count backwards. 4 is an even number, and so we count backwards by 2's. So we would have 4, or we may have 2, or we may actually have none. Okay, we may have 0 positive real zeros. It just depends on how many imaginary zeros are included in the zeros list for this particular polynomial. Now let's go on and find the negatives. Okay, what we have to do is change the P of x to P of negative x. That's very easy. Again, anywhere that you have an even exponent, the sign's not going to change when you plug in negative x, but if you have an odd exponent, it is. So 5x to the 5th becomes positive. 3x to the 4th will not change. Negative 2x squared, that's not going to change either. X squared there is an even power on the x, so when we plug negative x in, we'll still stay negative. And then the last one's not going to change either because it's a constant. There's nowhere to plug the negative x in. Alright, so take this and recount. We've got a positive to a positive. That's not going to be a sign variation there. And then I've got another positive to positive here. But then we do a positive to a negative, so that's 1 sign variation. And then that negative to a positive term next. So we have only 2, okay? So the number of negative real zeros will be at most 2, okay? It'll either be 2 or less than that, but an even number, so 2 or 0. Now what we didn't see here is we didn't count and get an odd number. If you count and get an odd number, say we get 5 sign variations, then there's 5 or 3 or 1. You still count backwards by 2 each time, even if you start with an odd number of sign variations. Okay? So that's how we tell how many we have. Now, this is not a particularly fantastic result here as far as being useful, okay? What we really kind of want to see when we do Descartes' rule of sign for a problem is we want to find out that either there aren't any positive real zeros or there aren't any negatives, okay? That's a good result because what it does is it halves the list that we had when we made out our rational zeros theorem list. We would not have to worry about checking any of the positive real zeros or the negatives depending on which one we found to be 0, okay? But in this particular case, both have values, so we know there may not be negative real zeros or there may not be positives, but there's no way to tell that for sure at this point. So a result like this really doesn't give you a lot of help in the long run, but it's still a worthwhile thing to look at while you're trying to find the zeros of a polynomial.